Hello and welcome to the final part of this convolutional neural network series. In the last video we trained a CNN and talked about different CNN architectures. Today we will have a look at some advanced topics in deep learning, which are transfer learning and explainable AI. In the previous part we trained a simple CNN model, but the performance was not really good yet. I made the point that we don't need to come up with our own CNN architecture, but instead can reuse existing state-of-the-art CNN architectures. This means we can, for instance, use a ResNet 50 and train it with our dataset. But usually training such models is computationally expensive and hence takes a long time if the hardware is not powerful enough. Therefore, we go even one step further and use so-called pre-trained models. These are models that were already optimized by other people, and we just transfer the model, including its learned weights, to our use case. Transfer learning is a machine learning method where a model developed for one task is reused as the starting point for a model on a second task. If we use a model that has been trained on the ImageNet dataset, then this model can be easily transferred to any other image source, as in our case the 7 wonders of the world. Why is it possible to reuse models? We've learned that the first layers in a CNN learn low-level features such as edges or corners. These features stay the same for different images. This means we always have to learn edges independent of what image dataset we have. As a result, we can simply reuse the learned weights of the first hidden layers in the network. The higher layers in the feature extraction part detect high-level features such as faces, cats, or other objects. As we have different things like pyramids or the Colosseum in our image, we should learn these layers from scratch. This means we can reuse most of the layers but also have to do some slight adjustments. This is also the case for the fully connected top of our model, as it uses the feature maps from the previous feature extraction part. However, we said that the pre-trained models are trained on the ImageNet dataset, which is a wide variety of different images. Therefore, it is very likely that the model is also capable of detecting similar high-level features. Hence, often it is only required to retrain the fully connected final layers of the network. We need to do this anyways, as for instance we only have 8 classes in our dataset. ImageNet has 1000 outputs. Using transfer learning saves us time and computing power, as we need to optimize way less weights in the network, and the rest stays untouched. The next question is, where can we find these pre-trained models? PyTorch provides us already with a lot of pre-trained CNN architectures. It is very easy to download a pre-trained model. We can directly do this in the code with this one-liner. We will see an example for this in a second. But it's not only CNN architectures that can be used with transfer learning, also other machine learning areas such as natural language processing or reinforcement learning use pre-trained models. The collection of these assets is often called Model Zoo, and there's also a website for this. In most cases, pre-trained models work very well, and therefore I recommend to always try out transfer learning first. So this is the website I just talked about, and if we enter PyTorch here, we get a large collection of different PyTorch models. And if you click on them, you get a short description what the model is doing, for example this generative adversarial network. Further down, you find a description how to use and install the model. Furthermore, you also find different categories here, so not just computer vision but also NLP or reinforcement learning. So it's a really great website to find pre-trained models. So now here we are back in our code, and we will use the augmented trained dataset we've defined previously. So we have some cropping, rotation, flipping, and so on. And there's one thing we need to add for all pre-trained ImageNet models, and that is normalization. So all images that were used for the training of these pre-trained models were normalized according to these parameters, which are pre-calculated on all the images. And that's why we also have to use them, of course, for our images. And then we define a batch size again and fill our training loader with this dataset. Next, we can define the model itself. And this is, as already mentioned, pretty simple by this one line where we download the pre-trained model. In our case, it's a VGG16. You can replace this with any other pre-trained model. I use the VGG16 because it has a relatively simple sequential structure. So you see it's a stacking of conv and pool layers, and then there is the output classifier part. Now, next what we need to do is we need to freeze all the parameters because we don't want to retrain them. This can be done with this loop, so we iterate over all the parameters and we say, okay, they don't require gradients to be calculated. Then in the last part, we need to replace the fully connected top of the network. So in our case, we have 8 output classes. That's why we replace the output layer with the, so here we first get the number of features for the last layer, and then we override this last layer, which is the layer at position 6 for the classifier part. So that's 1, 2, 3, 4, and so on. That's this last layer. And then we replace it with 8 output classes instead of 1000. And now in the forward function, all we need to do is we need to pass it through this pre-trained model, and only the last part will now be adjusted in the learning process. So having a look at our overall structure, here is the feature extraction part, and secondly we have the classifier part of our CNN. So now we are ready to optimize the model, and that's why we create another optimizer here and pass the network parameters. And now actually the only part that needs to be trained here is again just this final linear output layer. You might want to play around with training also those, or even some of the convolutional layers, but in this simple example we'll only retrain the final part of the network. And here we just need to train 8 epochs, as we don't have many parameters we need to adjust. And you see the loss is decreasing as well as the train loss. And if we print the result of this again, we see, oh, okay, we already achieved to almost classify all of the images correctly. And let me tell you, if you use a res-next 50, for instance, you get pretty much 100% for each of these images. So it's super easy to use pre-trained models, and in most of the cases they achieve really good results. Now let's talk a little bit about explainable artificial intelligence. Soon I will also make a full video series on this topic, as it's very exciting and interesting. Explainable AI has the goal to better understand and interpret machine learning models. For most data scientists and machine learning engineers, the models they build are black boxes for them. They might have a great accuracy and produce the right predictions, but do they really work as intended? Do the models use the right features, and are they robust against special inputs? Usually there's a trade-off between the interpretability of a model and the performance. A simple linear regression model can be easily interpreted by looking at the impact of the learned coefficients. Unfortunately, linear regression does not perform very well if the problem is getting more complex. Neural networks, however, can learn many non-linear relationships, but cannot be easily interpreted by a human. There are so many weights as it's simply impossible to directly understand what the network is doing. So from a data science perspective, explainable AI helps us to debug and better understand the models we build. In explainable AI, or interpretable machine learning, exist a variety of different algorithms. Have a look at this overview. There are techniques to understand the feature importance, explain individual predictions, and create visualizations that help the human to better understand its model. For this video, we want to gain a better understanding of CNNs, which means we look for algorithms that can work with image data. In the Explainable AI series, we will also have a look at other possibilities and dive deeper into this topic. For the following, I have picked out 3 algorithms we will implement. But don't worry, of course, we don't have to write the code from scratch. First, we simply visualize the filters, or more precisely, we visualize what our filters look for, so the visual patterns in the image. After that, we will use a method called GradCam, which helps us to find out the areas with the highest activation in the input image. Finally, we will use a technique called Adversarial Attacks to test the robustness of our models. These 3 methods were mainly developed for neural networks, more specifically convolutional neural networks. For all of these models, we will use the VGG16 model, as it has a simple sequential structure that makes it easier to iterate over the layers. When it comes to visualizing the learned filters in a CNN, we have mostly 3 possibilities. Option 1, we plot all the filters we applied in the different layers. For instance, 64 of these small 3x3 kernels. Option 2, we can also plot the activations, so the feature maps after each layer. Finally, there's another technique proposed 2009 in the paper, visualizing higher layer features of a deep network. We can also construct an image that leads to a high activation for a specific learned filter. This means the pattern the filter looks for occur at many places on a generated image, like these circular shapes. Now the first option of visualizing the kernel matrices might help us on a low level, but once the filters are combined in a higher feature space, visualizing a lot of small filters won't really help us. The deeper we go, the more high-level features we get. In the following, we will therefore choose option 3, as it shows the high-level features a specific layer is learning. I found these approaches in the blog posts linked below. So the way how this works is pretty simple. We start with a random image. This means we have random color values. Then we input this image into our CNN model, so we pass it through the convolution and pooling layers. And once it arrives at the layer we're interested in, we select the activation map we want to investigate. So we have two things to specify here: which layer we want to visualize and which filter, so which feature map. And now the cool idea. We simply optimize our input image so that it leads to a high activation for this specific feature map in the selected layer. In other words, the color values in our input image are now the parameters we want to optimize, just like the weights in the neural network. And the loss function is simply the negative mean of the activation values. Using gradient descent, we can optimize the input image with respect to the activation on that feature map. The higher the activation, the smaller the loss will be. A small side note, in the original paper they use gradient ascent on the activation. This means they define a maximization problem. But here we simply put a minus in front of the loss function, so we can also use gradient descent. After several iterations, we end up with an artificially generated image that displays the visual pattern a filter is meant to respond to. In this example, the filter looks for circular shapes. Now let's go to the code and apply this as well. I mentioned earlier that there exists a library we can use. Unfortunately, we cannot install this with pip. That's why I copied most of the things into the code here. All it contains is just a couple of functions, a preprocessing function that standardizes our image according to the ImageNet dataset. We've seen this before, and it's also converted to a float tensor. So that's basically our preprocessing pipeline. And then there exists a second function, recreate image, which normalizes the image back. So it does basically the reverse operation, and it also converts it back to a NumPy array. And then in this main class, CNN layer visualization, we have this function visualize layers with hooks, create a random image, and then pass this random image as a set of weights to an atom optimizer. And now all this code does is pass this randomly generated image 30 times, so 30 iterations, in a forward pass layer by layer through the model until we end up at the selected layer, so the final convolution layer we are interested in. And then, as already said, we take the negative of the mean of the activation map from this final convolution filter. And we use that as our loss function and backpropagate the loss to our image, so adjust our image accordingly. So as mentioned earlier, we need to specify which filter we want to visualize. I mean, there are feature maps of, let's say, 64 different filters we applied, and of course we can only visualize one at a time. Now, if we look at the result of this, we see that the first layers, so this is the first convolutional layer, respond to single color values, and afterwards we start to get more high level. We have edges, we have special shapes here, and if we proceed over the layers, we see the things get more and more complex. We already have some quite high level shapes here, and other very interesting things. Here are the circular shapes we've seen before. And for example, if you look at this, it looks for these kind of circular patterns. And if we have a look at the Taj Mahal, you find these shapes at the top of these towers. So that's certainly something the filter might respond to. And if you go further, these things get even more high level. But I think you get the idea. So we can visualize what the filter is looking for in our image. Let's continue with the next method. Gradient class activation mappings are a way to visualize which region in the input is most important for a prediction. This means GradCam helps us to understand where our model is looking at in the input image. For instance, for a Taj Mahal prediction, the most important area should of course be the building itself, and not for instance the heaven or people in the image. This helps us to validate if the model is working properly. The way how this works is that we simply pass the image through the layers in order to calculate the feature maps in the feature extraction part of the network. Passing those further through the network, we get the prediction. Using this output, we can now calculate the gradients of the classification with respect to each activation map. What this simply means is that we backpropagate the impact of each feature map to the specific prediction, for instance Taj Mahal. This can be done as displayed in the second part of this formula. YC is the prediction score for a specific class C, such as Taj Mahal, and AK are the different activation maps. Additionally, global average pooling is applied on all of these calculated gradients, which is done in the first part of this formula. That just means we take the mean of all values for a specific feature map. What we get is an importance score alpha, and that for each feature map in that specific layer, for instance the last convolutional layer, and this alpha tells us how much a feature map impacted the prediction. Now as a final step, we simply multiply each of the feature maps with the importance score, which is nothing else but a weighted combination of the activations. Additionally, we apply ReLU activation to cut off all values below 0, as we are just interested in the positive activations. So maybe this sounded a little bit complex. To summarize it, the basic idea of GradCam is to use the gradients to create weights that tell us which activation map was most important for the prediction. And by combining all of them, we end up with a heat map that tells us which areas of the input led to the highest activation for a specific layer. Just a side note, there exist also other interesting approaches that go into a similar direction, for instance layer-wise relevance propagation. Now let's apply GradCam to our CNN. So again, here we have the code from the repository I showed previously, and in this first part we have two main functions. One of them does a full forward pass, so this simply passes the image through all layers to get the output, and then we have a forward pass until a specific layer we are interested in. For example, we want to visualize the importance score for layer 16. So we just pass the image until layer 16 and get the feature maps. And now in the main part, all that is happening is that we perform those two forward passes. So we have the model conv output, which is the output of the convolutions at a specific layer, and the model output, which is the final output of the model, so our prediction. And now, as said on the slides, we calculate the gradients with respect to the specific feature map. This is done in this backward pass here. And after that, we take the mean of these gradients, which means we summarize the gradients for one of those feature maps. And in the final step, we multiply this weight with the feature map itself, and we get the heat map we were looking for. So in order to apply GradCam, we now first have to choose an image. I chose this Taj Mahal image, and we convert it to an image, preprocess it according to the ImageNet dataset, and then we can simply calculate it using this generate cam function we've just seen. And again, we have two things to specify here. First of all, we want to know the activations for a specific class, and as we have a Taj Mahal image, I will put a 7 here, as this corresponds to the class number 7. And then, secondly, we need to specify which layer. So the question here is which layer we want to visualize, because the lower layers will usually have smaller activations, so more precise activations, and the higher layers will have larger areas because of the growing receptive field. So this code is just for the visualization. It's not too important, so I won't go into detail here. But essentially we get this output. So that's the heat map for this layer 28 applied on this. So this means this building and this section in front of the building is most important for the prediction for class number 7, which is Taj Mahal. So if we do the same thing for a lower layer, so 20 instead of 28, we see, okay, lower level features are important here. So it looks for those towers and generally smaller parts of the image. So what we've just seen totally makes sense, because we want the model to look for the building and towers and so on. And I found another example which is quite interesting. If we again select the last layer and the pyramids, we see that the model basically just looks at these people. And actually, we don't want the model to look at the people, but instead the pyramids, of course. And that's a way to see, okay, the model is not working perfectly. We need to find more data and make the model generalize better to avoid that the model is using the wrong features of the image. Finally, let's quickly have a look at another interesting method. To summarize it in one sentence, adversarial attacks generate model inputs, in our case images, that are misclassified by the model. The idea is to perform minimal changes on an original image, so tweaking a couple of pixels here and there so that the model prediction is changing. Mathematically, this is a simple optimization problem. X prime here is the adversarial example that we want to generate, and X is just the original image. Now, the objective of this optimization problem is to minimize the difference between those two, as we want minimal changes on the original image. This difference is usually measured with the Euclidean distance, so simply the squared difference of the pixel values. Let's quickly recall that a neural network is nothing else than a function that maps inputs to outputs. Our constraint in this optimization problem is that the output, so the prediction of our model, is different for the adversarial example. So plugging in X prime and the original image X should lead to different classes. In this example, the model predicts Chichen Itza in Mexico for the adversarial example on the left. By the way, the Chichen Itza looks like this, so it's clearly a false prediction. We can also specify a target class here. For instance, we say, change this image to make the model predict Taj Mahal instead of pyramid. That is called a targeted adversarial attack. Now, as this is just another optimization problem, we can again simply use an optimizer and use the gradients to create X prime. And that's exactly what we will do in the code. We adjust the original image according to the gradients until it fulfills the constraints. The changes compared to the original image are usually also called perturbations. In the best case, you won't spot a difference between the two images. Here in this example, you will recognize slight changes in the sky of the left image. Let's do it in the code to have a closer look. So this is the code for the adversarial attacks, and again this comes from another repository which is linked here. So this code is pretty simple. All it does is taking the original image, pre-processing it and putting it to an optimizer, so as a set of weights or parameters. And now all we do is we pass this image to our model and we get the output of the model. And now using this output, we can calculate the loss. So how far are we away from the target we want to predict? For instance, we have a pyramid image and we want to predict Taj Mahal. So this loss tells us how far we are away from the target class we have specified. And we do this in a loop of 500 times until we reach the target confidence. Let's say we want the model to be 90% sure that it's the Taj Mahal instead of the pyramid. And using the backward function and the optimizer, we can now adjust this input image according to this loss function. And again, if we execute this code, so I've selected this first image, which is the pyramid, we pre-process it again, and then we use this fooling sample generation to generate our adversarial sample. At first, the confidence for the target class, which we have specified as Chichen Itza here, is very small, only 0.00 and so on %. We see it starts to increase the probability until we reach the 90% confidence here in the 13th iteration. And if we look at this, we see that's the original image and that's the generated adversarial sample. And plugging in those into our model, we see this original image leads to class 4, which maps to the pyramid. And if we plug in the second image into our model, we see we get a prediction of 0, which maps to Chichen Itza. So we see for this second image, which has some small perturbations in the sky here, we get a totally different prediction. So we have fooled the model here. Or here is another example. We use a Chichen Itza image now, and we want the model to predict that it's a pyramid, so the other direction. And here we see we only need 8 iterations, and this is the original image. This is the adversarial sample. You see again some modifications here, and I mean that totally makes sense. A pyramid would have like a pyramidal top here, and by adding some pixels here, the model might think, okay, that must be a pyramid as it has such a top. So what we've just seen is that the model starts with a very certain prediction for a pyramid, as the image contains the typical visual patterns. As loss, we then use the difference between this probability distribution and our target class. The gradients then tell us how to adjust the pixel values in order to shift the distribution towards the target class. After several perturbations, the model certainty starts to change. It's not sure anymore if it's really a pyramid, as there are for the model confusing patterns on the image. Finally, we end up with a slightly adjusted image for which the model gives a wrong prediction. It has been fooled. So overall, this method helps us to figure out if our model is robust against such attacks. Of course, there also exist ways to improve the robustness of the model, but we've now reached the end of this CNN series. Congratulations that you made it through. I hope this was helpful and interesting for you. As already mentioned, I'll soon create an Explainable AI series, which addresses many other interesting topics, and I would of course be happy to welcome you there as well.